So
permission.
Miles, I made you the host, and okay, and you're doing the
Wonderful.
recording. You could either
Yes,
do it on the cloud or something like that.
I'm recording it on my computer.
Sounds good.
I kind of
Cool.
wish it would let me choose where to save it because I got some small drives on some places, but that's fine. All
All
right.
right.
So, uh, first off, leading off with this, I cannot teach you all of Ansys. I do not know enough about Ansys to tell you about everything it can do. However, the focus of this is going to be on getting familiar, at least with how to work with Ansys and a bit about meshing. And we're going to do that through the use of the static structural element. So what I've done beforehand, and if any of you have downloaded the workshop or the Ansys student version, it is I will be sending out a step file for running this workshop with and kind of learning using a part. So let me navigate to that and I'll put it in the workshops channel on the Discord. So I went ahead and I made a CAD model of an ASME flange, which kind of gives a good feel for every aspect of Ansys. You could imagine having a thermofluid running through that flange, and you could see what the pressure loss is, how much heat is being transferred over, what the pressure does to the walls. We're going to really simplify it and just treat it as pressure on the walls. And that way we can just kind of mess around with the details of running uh, the Ansys stuff. So when you have the student version downloaded and installed, you want to search for the program Workbench on your computer. It has no labeling of being Ansys whatsoever, and it took me ages trying to find it in my file structure. Just click down here and search Workbench, and it'll work, hopefully. Uh, the part I am putting in the Discord now, it is in the workshops channel. It is a step file. When you're working with Ansys, first thing is do not use the built-in CAD program SpaceClaim. It's terrible. Uh, this I made with NX, and it can take NX part files. However, it's even easier to import step files. Sometimes the part files, you have to reopen them in SpaceClaim, and since SpaceClaim is so bad and takes so long to boot up, you want to avoid using it wherever possible. So I've sent a step file there. You can do that in NX by either exporting as a step file or saving as a step file. Either is fine. On the left of this menu, is all of the different types of analysis systems that you can do with Ansys. There's a lot of them, and as stated earlier, I don't know all of them. Uh, the ones that we've used that I'm aware of, I know that Turbo's used one of them. I imagine it'd be Turbo Machinery Fluid Flow, but I'm not too well versed on it. There's transient thermal, which we've used for some of the nozzle stuff for Molehill and Fuji. And we've got static structural, which is pretty commonly used for working with loads. There's also Fluent up here for fluid flow. That is heavily used in any group that's doing detailed fluid design, injector in particular, I'm aware of. But Fluent is one of the most complicated tools in Ansys, and I cannot teach that in a reasonable time frame without first going through details of meshing. It's a lot. So we're going to stick with static structural. And to get something into the project environment, you just click and drag the type of system that you're doing to one of the green squares. There's more as you place more systems. And we've just started up a static structural system. We can then right click on geometry and not new space claim geometry, but instead importing geometry. And I've got the test flange file already loaded up previously. So we're going to go ahead and use that. And before we go and start setting up the model and learning about meshing, when you're working with structural or thermal sims, you need to define the materials that are being used in the sim. So to do that, you double click on engineering data, and you can either manually enter tables of properties, which is a pain, or you can go to engineering data sources up here in the top left, where there's a whole bunch of different categories of materials. that are straightforward to add into your system, and they automatically have properties included. We're going to use general materials right now, just because they're pretty easy to work with. Double clicking on the name there will load it up. And the properties I've got for these is for stainless steel. So we're gonna use stainless steel, and we're gonna check the failure pressure, or the rated pressure of a class 300 flange made of stainless steel. So I've clicked plus on that, and if I now click engineering data sources again, it brings me back to the menu where it shows all of the different materials, and you can see there's stainless steel and structural steel. We can remove the structural steel, but we'll leave it in to show where you actually set the values. So you can click on project in the top left again, and it'll take you back to this screen. And now we're gonna go into the model and get into the bulk of what Ansys requires. So Ansys is a computational solver. And in order to solve in 2 or 3 dimensions or whatever it is, you can't just work with random sets of analytical equations in all cases. So Ansys works with what's called a mesh. The body that you're performing the analysis on is split into many, many thousands of cells that each of them have their own boundaries and their own volume, and properties are measured between them. So rather than dealing with infinitesimal quantities, it's looking at the basically the flow in and out of cells, or the stresses in or out of cells, to find a solution to the differential equations or whatever else you're working with. However, you have to kind of give it instructions on how to make that mesh, and the quality of the mesh is hugely important to how well the simulation will work. Ansys, if you have a bad mesh, the whole simulation is bad. And related to that, because the quality of the mesh is so important, never, ever put people in a dangerous situation with a part if you haven't tested it in actuality. Don't trust an Ansys sim. Always perform tests to qualify your parts and verify your models. That's the #1 reason for testing. Once you've done a simulation on one kind of part and verified it, then you can have a little more trust, but always test and verify the models and make sure you're not missing something. So first off, how do I even navigate in Ansys? Well, Ansys loves mouse buttons and the control key. If you middle click, you spin it. If you control middle click, you pan it. And if you right click, you can zoom in like that, or you can use a mouse wheel. And clicking will actually select a kind of edge or face or whatever. The kind of thing it selects, there's a set of buttons up here where you can choose what selection mode it's in. So if I wanted to select the entire body, I could go to here, select body, and then click the whole flange and it selects it. Another option, if you want to select multiple faces at once, you can hold control while you click, or you can click and drag over all of the selections, or both. And that lets you select multiple faces at once for assigning varying things. One thing that is useful is you can name selections. So we might go ahead and take this whole selection right here and right click on it, and down here create named selection, and we might call this outside, if I can spell, where this is the outside of this part. This is a part that's not going to be either fixed in place or have pressures applied from the internal fluid. So we can assign that, and then when we're later working with assigning the boundary conditions or the loads, that's really easy to go back to and say, I want the outside and I want to apply this pressure there. So that's a really useful thing. It's not necessary in all cases. A part like this, it's not entirely necessary, but if you've got really complex geometry, it can help a lot. So now, before we get to meshing, you can also set the material by clicking on the drop-down for geometry in the outline on the left here. And the part itself has a material in this bottom left. This is where it gives the details of whatever you got selected in this outline. And the material down here, it's currently structural steel. We're going to switch it to stainless. And so you just, every bit of work that you're doing in Ansys, you're going to select what you're editing from the left. There's going to be a detail panel. In structural and meshing, it's usually down here. Fluent, sometimes it's over here. And in that panel, you change the settings that'll affect the mesh or the actual solution that it's finding. So we've set the material to stainless steel, and now we're going to go to the mesh. Right now, it just has base settings, and we can go here and click Generate Mesh on this ribbon bar up here, and it'll run, and it'll make this. So this is a very bad mesh. For one thing, we can just look at these circles and see how distorted that is there. That's not capturing the actual shape of the system. So already that's a sign that we have problems here, and we would like to improve the quality of the mesh. However, rather than just relying on qualitative stuff, there's actual quantitative variables that we can look at to determine the quality of the mesh. And to do so, if we have the mesh selected and we go to quality, open that up, and then change this mesh metric to, there's a whole bunch of things in here, but the most important for most meshes are skewness and orthogonal quality. Skewness is how much the mesh, how much a cell differs from a neighboring cell. So for example, that cell there that I'm pointing to, how much it differs from this cell is kind of a rough measure of its skewness. It's a little more complicated than that, but you want low skewness cells because it makes them more regular and therefore the results are more accurate. It gets you closer to that infinitesimal solution. And we can click on the skewness here, and it also gives us a lovely plot down here where we can also select, say, a grouping here and see our very highest skewness cells. And you can see they're down here on this section where the mesh, if I can get it to not show that anymore. There we go. You can see the structure kind of juts out a bit, and that's where the flange is meant to seal together. Because of that shape, it's made these really, really long, flat tetrahedrons, and these don't simulate well. So we want to avoid those. Ideally, you want your skewness, your maximum value of skewness, which you can see in that detail panel, to not be over 0.9. The lower that max value is, the better, but over 0.9 is probably a sign of a bad mesh, and you'll probably not get good results. The other important metric is the orthogonal quality. So this is more about how distorted the cells themselves are. So whereas skewness is about their relation to the nearby cells, the orthogonal quality is more about the shape of the cell itself. So once again, we're looking at a whole bunch of cells. These are the best quality cells. So you can see all of them are very, very regular tetrahedrons. They're quite large, but that's not necessarily a sign of good quality. But they're extremely regular, which is a huge benefit. However, our lowest quality are, again, in there, where they're very, very narrow on one face and very broad on another. Not very good. You can see another example here of this frankly dreadful tetrahedron that's just kind of shoved in there. So the first challenge is, how do you improve that quality and that skewness? There's a whole bunch of tools that Ansys gives you to improve the mesh, but you have to do almost all of it manually. One that's fairly straightforward for getting started is you can set a method. You can either do that by right-clicking here and inserting a method, or up in this ribbon bar, they've got a whole bunch of different things in. A method is how you define what kinds of cells it's going to make. So rather than telling it just letting it choose whatever it's going to do, you can select the body that you want to set this method for by selecting the body in the panel and then clicking on geometry and apply. And then you can choose, rather than automatic, you can choose what kind you want. There's a lot of different cases where you want a lot of different kinds of meshes. So in most cases, you're going to want to figure out what works best for your condition. I cannot promise you a catch-all solution because every problem is different. In most cases, I've found tetrahedrons to be useful. And so if we just set that to tetrahedrons, there's now this algorithm of patch conforming or patch independent is the other option. Patch conforming builds from the inside of the structure out. I found it very useful for thermal sims and structural sims where the boundary conditions are a little less important than the interior. However, patch conforming is very bad for fluid sims where you need that wall effect and those boundary layers, and patch independent effectively builds from the outside of the structure inwards in the algorithm. It has a lot more settings to put in, including a minimum size limit. You can set all sorts of different details. We're not going to use it for this though, because we're doing a structural sim and patch conforming will do the trick. So if we try generating the mesh again, we'll see that it's not that different. It's probably the same mesh. It was probably using tetrahedrons to begin with, but now we've locked it in place for using that, which allows us to get a lot more consistency. The next thing to note is that a lot of these cells are very big, and that's a big part of what's losing us the quality of these circles. So there's a few ways to do it. One is a refinement. A refinement will basically take a surface or edge and force that to have more detail. So if we really, really wanted the detail in those, then we could set a refinement and it would make a lot of smaller cells near that edge. However, refinements tend to make for worse quality and skewness because when you apply them, they result in a lot of smaller cells transitioning to larger cells, which is messing with your skewness. And some of the cells to fit into that boundary where they merge together are very low quality. So ideally, you only use a refinement if the geometry of the mesh is not matching the geometry of your system. In this case, we're not too concerned right now. The better effect for reducing skewness and improving quality is a sizing. So we'll go ahead and insert one, and we can select the body that we're applying this sizing to, and you can split your part into multiple bodies and assign different sizings on different portions, whatever works. There's also a lot to be said for symmetric parts. We could split this part in half or even in quarters and only simulate 1/4 of it, and it would still be roughly accurate. But we're just gonna stick with a rough idea of what's going on here and just use a sizing on the whole body. Now, right now, the default sizing is 9 times 10 to the negative third. I've found that steadily reducing this value allows you to kind of check the quality and the skewness as you go along. So if we set this to 8 to the negative times 10 to the negative third and generate it again, it will run real quick, and you can see this mesh already looks neater. It's a lot smaller cells, and the cells look a bit more regular in some sections. And if we actually look at our quantitative values, you can see our minimum orthogonal quality has already gone above 0.1. Just barely, but it's gone above. And the maximum skewness has just barely dropped below 0.9. So if we're looking for the very minimum, this mesh would be enough. However, that's still pretty high skewness for some of our cells, and it's pretty low orthogonal quality for some of them. So we could keep making this mesh smaller. However, the smaller the mesh, the more cells you have, and the longer it takes to simulate. I'm going to just make it a little bit smaller. We're going to set it to 0.006 and generate it, and you can see just the quality that we're going to get out of that. And it's not a huge improvement necessarily over the 0.8. You can see the orthogonal quality, the minimum's only gone up about 0.06, and the skewness has only gone down a little bit from just barely 0.89 to 0.84. It's moved the averages over a lot, which is good, but just note that there's a kind of a limit to how much of an effect you're going to get, and it's usually these worst cells that are going to mess up your solution the most. We're going to stick with this because it'll give us a good balance of runtime and detail. Before I continue, any questions about meshing? Nope. All right. So we're going to move on now to actually setting up a simulation. So now that we've got the mesh set up and we're satisfied with the quality of it, we can jump to the analysis setup. So first off, in a structural sim in particular, you need to define supports. Without supports, it just kind of doesn't know what it's actually doing in the world, and it could apply a pressure that just causes it to like shoot up into the sky or something stupid. So it requires supports to actually solve the system. We're going to use fixed supports. And in particular, this is a weldable piece, so we're going to treat this as a fixed support. That may not be a fair assumption. However, just for having supports, it'll work. And we're also going to treat the bottom face as fixed. Think of this as being connected to a solid block on either side. We're just testing the failure of the part and not of the parts it's connected to or the seal itself. So this is where we'll put our fixed supports on. Very seriously consider where your fixed supports are on your actual parts so that we can make sure that we're not making very bad assumptions in our analysis. This is kind of a critical step. The next thing we're going to add is actual pressures. So first off, we're going to assume this valve is in the atmosphere. And so we need to apply the geometry first. And we made that named selection of the outside earlier. If we select that, by right-clicking and selecting the items in the group, and then go to the pressure and apply that as the geometry, now it will actually apply the pressure on that selection we made earlier. So if it's really hard in later portions of the sim to get down into the details, having named selections to get things set up ahead of time is really good. Once we've got that pressure assigned, we can then assign the actual magnitude of it. I'm going to use atmospheric pressure because we're treating this as being in an atmosphere, and therefore we're just going to have that set pressure. And then on the inside, we're actually going to use, I have a table that I found, if I can just get it to open up, of the ratings of flanges of different classes, ASME flanges. Wonderful, thanks for that. And in particular, we're using a class 300. We're running it in this temperature range. So we're going to look at what is it like at this pressure rating of 720 PSI. Now, Ansys, I do not have it set up to use PSI. I have it pascals, and I don't even know if there's a way to change it because I don't understand Ansys enough. But we're going to go ahead and create another pressure, and we're going to apply it to this inside face. And now we're going to take the magnitude to be that 720 PSI, which I should have had written down, but I didn't. So I will look that up real quick. All right, it is 4,964 megapascal or pascals, 964,000, whatever. That's the number in pascals. That's been applied now on the inside face. So this is our loading on all of our different faces. We've got a fixed support on this bottom face and the little ledge on the inside there. We've also got a fixed support on this welding point. We've got pressure being applied to the outside. Usually this atmospheric pressure won't make a big difference at most fluid conditions, but just to be thorough, we can add it in. It could hide problems that already exist, but it's worth adding anyways. And then the interior pressure of the actual fluid in this flange. So now we've got all that made, and we can set up right now what we want it to output. By clicking on solution, we now have a different set of things up here. For now, we're going to look at stress and see if this flange yields under this pressure. So we can go to stress, and it has all these different kinds of stress. We're just going to use von Mises. It's accurate enough for this condition since we're dealing with a tensile material and stainless steel. But in certain conditions, you might want something like a maximum principle or something. We're going to use the equivalent von Mises. And if we now solve this system, it'll run the calculations, checking all of these different cells with the applied loads, and calculate the stress distribution. And it shows a very dramatically overscaled image of what is happening to the part. So the flange itself is not bulged out this much. If you actually did this test in real life, it does not look like this. However, in order to actually emphasize where you might have weak points, they kind of bulge it out more, those points that have more strain. We can see the scale on the left here of the pressures in pascals, or the stresses, and inside you can see that's where our maximum stress condition is, because it's right near our fixed condition where it's kind of bulged out from that fixed condition. And so there's this really tight bend suddenly, and that's what's causing this to be the stress concentration. Likely, if the part upstream were just as movable as this pipe, then that problem wouldn't exist. But it's just a good way to define this individual part and find its failure. That is about 20 megapascals for the maximum stress we're seeing. And stainless steel has a yield stress of about 210 megapascals. So this part is clearly within tolerances. Obviously, we expected it to be because that's its rating. But it's good to verify in some cases, but mostly just verify with parts that we're modifying in some way or that we are making ourselves. We can also instead have it display in terms of different, instead of just this sort of coloration of the outlines, we might want to see where the structure is on the inside. So we might change it from a geometry of just the exterior to something like isosurfaces, where now we can see all of the points in the surface where it actually matches these exact values. So you can see sort of those walls of the cells and where those forces exist. You can also change from the exterior, just having smoother contours for a bit of a cleaner image, or something like ISO lines to see just where the actual lines are on a face. And then we might want a different kind of solution. We might want to look instead at strain, where we could again do von Mises strain and evaluate the results. And you can just right click on the solution type and evaluate results, so you don't have to run the whole simulation again. And you can see here the strain's pretty similar, but the numbers are very small, which is exactly what we expect with this kind of loading. So that's the gist of it. That's kind of the gist of using Ansys structural. There's a whole bunch more to it. I cannot fully explain all of it in a reasonable time frame, but that's kind of what you'd be working with. Meshing is the bulk of the time, trying to figure out how to improve a mesh to improve the quality of a simulation result, because one bad cell can mess up an entire simulation. That's really bad. But with all that, are there any questions? All right. Well, that's all I've got to show for Ansys structural. Transient thermal is pretty similar. There's not a lot different to it. Instead of applying pressure loads, you're applying thermal loads. You have to apply probably a thermal material instead. It's pretty much the same thing, although there's a bit about it being transient rather than static, that you've got to set time steps and such. We can go through that another time if necessary. Fluent is way more complicated. Typically, if you're using Fluent, figure out a solution for your problem rather than trying to learn about every solution in Fluent. It's built for handling just about every fluid dynamics problem you could imagine. And in most cases, you're not going to need those things. So usually you're going to just be focusing on finding the solution for yourself and not for every problem you might have, at least at this level. So I think that's it then. That's a sort of brief rundown on Ansys and how it works. Of course, if you have any questions about this, feel free to ask anytime, and I'm glad to help. But yeah, that's the basics.
Thanks, Miles.
Thanks.
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 Yep.
Yeah, thanks.